In this video, we're going to look at the addition of primary and secondary amines to aldehydes and ketones. This is the synthesis of imines and enamines. So first, we need to learn some new structures here. So an imine is where you have a nitrogen double bonded to a carbon. And this is essentially analogous to a carbonyl. So imagine having an oxygen here instead. Now, in order for it to be an imine, you still have to have a lone pair on the nitrogen. And these R groups could be anything. So they could be hydrogens, they could be other carbons. But the important thing is that you have the double bond between the nitrogen and the carbon. And if you protonate it, this becomes what is called the iminium ion. Our next structure is the enamine. So this name comes from the fact that you have an amine and an alkene. Notice that the amine is one carbon removed from the alkene. So instead of having the double bond attached to the nitrogen, it is over here between what used to be your carbonyl carbon and the beta carbon. An imine is formed from the reaction of an aldehyde or a ketone and a primary amine. Before we go any further, I want to remind you that a primary amine means that there is one carbon attached to the nitrogen. That carbon could be secondary or tertiary, but it is one carbon attached to the nitrogen, and that makes it a primary amine. This reaction happens with a catalytic amount of acid, and you end up eliminating your carbonyl oxygen as water. So there are a lot of similarities between this and the mechanism for acetal formation. Now, one of the first things that you have to figure out is just where do we start, right? So unlike in acetal formation, where our first step was to protonate the carbonyl, we have to take a slightly different approach here because the amine is actually a much stronger base than the carbonyl. So if anything is going to get protonated, it would be an equivalent of the amine, which is probably going to happen. You're probably going to immediately protonate some amine, but that's not going to push us in the direction of our product. So remembering that this is a catalytic amount, which means there is a tiny amount of it present. So a tiny amount of our protonated ammonium is being formed. There's more amine left over. So the first thing that happens is the amine attacks the carbonyl carbon, and we push our electrons up onto the carbonyl oxygen. Don't forget after this step to balance out your charges. So this oxygen is going to have 3 lone pairs now. That's going to make it negative. And the nitrogen used its lone pair to create a covalent bond between it and the carbonyl carbon. That means it's going to be positive. So this molecule is actually neutral, which is why we're allowed to do this first step, is because we don't really create any sort of charged species. But from here, we are an acid, and we do have a fairly basic atom here. So if you go on the internet and you look at this mechanism, you're very likely to see somebody doing an intramolecular proton exchange. That's not particularly favorable. What is much more likely to occur is that the oxygen gets protonated either by the acid that's in the reaction mixture or by the ammonium that you've created. So we're going to show that in a stepwise manner. So we're going to take a proton away from that ammonium. And then our next issue here is that the nitrogen is still a charged species. So from here, the most basic thing that you have in this reaction is another equivalent of the amine. So it's going to get deprotonated by the amine. And this is part of the catalytic process. That proton is getting moved around as we go because it is the catalyst in this reaction. And this brings us to an intermediate here. This compound is called a aminal. It is analogous to the hemiacetal that we saw in the previous section. This is also called an amino alcohol sometimes. And there's really nothing super special about this. I'm just showing it to you because this just means that you're about halfway through the mechanism. So we know that the next thing we have to do is we want to eliminate the carbonyl oxygen because it's going to make its appearance in this water molecule. And this is analogous to the acetal formation mechanism as well. And we know that in order to do that, we need to protonate it. So what are we going to protonate it with? Well, we just created another molecule of that ammonium. I'm going to save us a little bit of time and just draw out an H+, but it's likely pulling it from the ammonium molecule. And this gives us a positively charged oxygen, which is going to be our leaving group. I'm going to redraw that arrow real fast. This gives us a carbocation and our amine next door. So the only thing that we have left at this point is actually to draw out a resonance form and then just do one last proton transfer. So we can create the double bond that we see in the imine by moving this lone pair down. And this gives us an iminium ion. We're so close, we're almost there. And then we have some water that we've created, or it could get deprotonated by another amine if you still have a bunch lying around. Pick your favorite at this point, and you've made it to your amine. So this mechanism seems kind of crazy, but it's very similar to the acetal mechanism. It's just where you had an alcohol sub in an amine, and then instead of adding in another equivalent of the amine, we just formed a double bond. So this one's actually a little more straightforward. And then this one is also reversible, just like the acetal mechanism. Now to get to the enamine, you have to use a secondary amine. So notice that we have 2 carbons attached to our amine here. That's what makes it secondary. And this mechanism actually proceeds almost identically to the mechanism of the imine formation. So imagine that we've gone through all the steps that we just did, right? We had the amine attack the carbonyl. We did some proton on, proton off stuff. We've eliminated our water molecule. Let's go ahead and draw an intermediate here so we can see something. So we eliminate this water molecule. And that brings us to our carbocation. This was the second or third to last step of the last mechanism. When we go to draw our resonance form, we create an iminium ion, but unlike in the last mechanism where we were able to solve that positive charge by deprotonating the nitrogen, we can't do that here. There's no proton on the nitrogen, and we can't just remove an alkyl group. So what we do instead is deprotonate from the beta carbon. We can pull off that last proton, and that allows us to push electrons up towards the nitrogen. So that is the only difference in these two mechanisms here. They both still make it to the iminium ion, but the next step is just deprotonating from a different location. So our next topic is Auxins and hydrozones. These are basically imines that are just made with more complicated amines. So for example, in this first one, we see a reaction with hydroxylamine. That's this molecule here. And we end up creating a double bond between the nitrogen and the carbonyl carbon. So this is kind of like an imine, but instead of having an alkyl group, we have this hydroxyl group. And you know that's going to have very different chemistry from having an alkyl group there. So this gets its own name. This is called an auxine. Now our next one involves reaction with hydrazine, which is something you've seen before when you learned about Wolff-Kishner. And in fact, this creates a hydrozone, which is the key intermediate in Wolff-Kishner. So we're pretty close to the point where we're actually going to go over the mechanism of Wolff-Kishner. I think it's the next slide, actually. So these are your two new functional groups, auxine and hydrozone. Okay, here it is. I think we learned this reduction like 3 chapters ago, and now we're finally going to learn how it actually occurs. So in Wolff-Kishner, the first step is to actually make the hydrozone. And of course, that takes several steps, so we're not going to draw out that mechanism. It's completely analogous to the formation of an imine. So we're just going to draw the hydrozone that would result from reaction of cyclohexanone with hydrazine. So here is our hydrozone. Now this is where the chemistry gets kind of weird and also really, really cool. So we have hydroxide. Base is one of the key things in this reaction. And the hydroxide is actually going to deprotonate the hydrozone, which creates a double bond between the nitrogens and actually forces the pi electrons from the hydrozone out to pick up a proton from water, which will have formed in the formation of your hydrozone. So that was kind of a lot, but what that gives you is a new intermediate where we have a double bond between the nitrogens. We have one hydrogen left on this nitrogen, lone pair, and we've accomplished the addition of one of our hydrogens. So there is an excess of hydroxide in this reaction, and also we have heat. So heat allows us to add energy to the reaction and push us towards things that might not be favorable otherwise. And this is one of those really cool things. So we deprotonate again. We create a triple bond between the two nitrogens. And this causes this bond to break and the electrons go onto the carbon. So now we have a negative charge on the carbon, and we've also created a diatomic molecule of nitrogen. This is just nitrogen gas. it is going to leave the reaction as a gas, right? It's going to bubble off. And this is actually the driving force of this mechanism, because every time you create this nitrogen gas, this is irreversible. This pushes you towards your product because the nitrogen gas is going to escape the reaction. And also, this is a very stable molecule. It's going to be very happy about that. And then we pick up a proton from water, and that gives us our final product. Note that when we deprotonate water, we create hydroxide, and since we're already in basic conditions, there's no reason we cannot create more hydroxide. So the other reason that this reaction is favorable is because it is entropically favored. We're creating nitrogen gas, which is going to leave, and spread out, which entropy loves, right? And we also got rid of this oxygen in the form of water. So we've actually created a lot of side products here. Anyway, that is the mysterious mechanism of Wolff-Kishner.